some water down there if you need it. Okay. Good afternoon, good morning. How are y'all? Everybody okay? My name is Jim Peoples. I'm with GrassRoots Marketing, Inc. Last time I was here, I was with Lockheed Martin. And last June, I happened to call my retirement people. And the lady gave me a little bit of additional information. She says, "You can retire in June if you like." And I said, "Oh, really?" So my wife had been running this market research company for 10 years. So I asked her if she'd pick me up if I were on the street, and she said she would. So I joined GrassRoots Marketing in August when I left Lockheed Martin, where I did really fun work in advanced concepts. And so now GrassRoots Marketing, which is a full-fledged segmented marketing company that does in-depth analysis of all kinds of things for all kinds of companies around the world, now has an advanced concepts group. For, I would say, 10 years, I've been watching what I would consider individuals and groups that are unlike any others. I generally ferret these people out in the physics and science world because I thought that's where the breakthroughs were going to come from. They weren't going to come from mainstream universities. They weren't going to come from mainstream companies. They were going to come from what I'm going to call technologists. And if you're in this group, what happens is the only way to get in is to get an invitation. There's no way to join them. They have to ask you to join them. So I set about talking to people about some of our ideas, and I created a group with the help of the president of Lockheed Martin called Lightspeed, and it was aimed at advanced manufacturing concepts for aerospace world. And that led to looking and thinking of advanced concepts for manufacturing of bio things, as well as organic and inorganic things. And that led to some additional friends that I met along the way, a guy named Paul March, who was working at NASA, who introduced me today to the person I'm going to introduce to you today, Dr. Jim Woodward from Cal State Fullerton. Did I get that one right?
That's right.
Okay. Dr. Woodward has been working for a number of years on something called Mach-Lorentz thrusters. I went out and looked at every unusual propulsion method on the planet, literally around the world. We did a canvas and we did a research. And the only thing that, in my mind, was real was Dr. Woodward's work. And the reason is it's based on regular physics. There's no new physics. And when the physicists in my group and the physicists in New York and other places reviewed Dr. Woodward's work, they couldn't find any hole in the bucket that we could find in a lot of the other systems. So Dr. Woodward and I have been communicating and engaging in conversations for a number of years. I invited him to our 3 different roasts at my facility, the Lightspeed facility in Fort Worth. And a roast is where we invite in someone who has an idea, and we bring both pro and con professors from everywhere that we can find them. And we let the speaker deal with it for 8 hours. And it's sort of like, Jim, when you're talking about art, if you've ever been to a review of your art, the art people put up with a lot more criticism on a daily basis than an engineer or a scientist, because the art student gets critiqued on a daily basis about his personal things. And so I decided to take that concept and bring it to science and technology because I wanted to find the truth sooner rather than later. And so we have what I will call ground truth from my point of view. And so we're very interested in advanced concept at GrassRoots Marketing in Jim Woodward's MLT, Mach-Lorentz thrusters. So with that, I'm going to ask Jim, if I had an MLT like this, what would I do with it?
It would be a bit thicker than a piece of cardboard.
Okay.
But a Mach-Lorentz thruster of that size is roughly the size of the test devices that I have running in a laboratory. And at the power and frequency range that they are currently being operated, they produce on the order of about 100 micronewtons of thrust. That's in CGS units for old timers like me. That's 10 dynes, okay, or 10 milligrams, which isn't very much thrust. If you optimize the device, made it higher power, higher frequency, that sort of thing, you could produce 10 to 100 times as much thrust in a device that size. Now you're talking about practical levels of thrust.
Yeah, practical for whom?
For things like satellite position stationing, orbital reboost of small satellites and things of that sort.
Why would I be interested in doing that?
Because if you have to do it with propellants, propellants eventually run out. With a Mach-Lorentz thruster, all you need is some solar panels to provide the energy to run it, and you never run out of propellant.
I see.
Yeah, let me explain.
Okay.
Okay. As the winner of the prize earlier this morning for understanding what Mach's Principle is about noted, Mach's Principle says everything in the universe is connected to each other. And in fact, the way in which that takes place is through the gravitational field, primarily. If you've come through a physics education, what you'll find is that the strong and the weak nuclear forces operate at the subatomic level. Electromagnetic forces are normal everyday scale sorts of things. But at cosmological distances, the only thing that's really important ultimately is gravity. Okay? And what Mach's speculation was that because we observe locally that we're not rotating with respect to the rest of the matter in the universe, is that that must mean somehow the rest of the universe is connected to us here locally. Einstein used this as a guiding principle in creating general relativity theory, though he was unable to formally incorporate it, at least in his view, into the final theory. And it's been a speculative idea that's been around for, as you can see, over 100 years. If you accept the idea that stuff here is connected to stuff out there via gravity, then the obvious question to ask is, well, gee, can you do anything that takes advantage of that fact? And basically what I've done is I've just sort of stood a standard procedure, reversed it. Instead of saying, here are some sources, what are the fields? Here's a field, what are the sources? And it turns out when you do that in a relativistically invariant fashion, what you find is that if you accelerate an object, but a special type of object, an object that stores internal energy as it's accelerated, which is a fancy way of saying it squishes when you accelerate it. Okay? The squishing itself produces a transient fluctuation in the total mass of the system, not in the masses of the elementary particles and things like that, as some people have incorrectly concluded. But the whole system, the mass changes just a little bit, but only while you're accelerating. But if you do that, what you can do then is while you are inducing a change in the mass in the system by doing this acceleration, you can act on it with another force and use it as a propellant. You push on it when it's a little bit heavier, and then when it's a little bit less massive, you pull it back.
So you have two plates and you have something oscillating between them.
Yes, and this is where I connect up with the next talk. That is to say, the futurist and science fiction aspect of this. The way in which you practically do this, the things that I have running in the lab, is you use capacitors, electrical devices which have some plates with a dielectric, some material in between, and you apply an alternating current or an alternating voltage actually to the capacitor, which causes the material in between to reverse polarization at whatever frequency you apply the voltage. Okay, so we've got a capacitor. It turns out that when you do that, you're storing internal energy in one of these things, and that produces this fluctuation in the mass that's predicted by Machs Principle.
And so then I stick something over the top and harvest that fluctuation.
Yes, what you do is you wind a coil around the capacitor, and you use the fact that while the mass fluctuation is taking place, that there is a current flowing through the capacitor. It's technically called a displacement or polarization current. And you act on that with a magnetic flux produced by the coil. And that, of course, leaves you with a flux capacitor. Okay? And flux capacitors produce small amounts of thrust. They don't take you back to the future or anything like that, but they do, in fact, produce this small effect.
Take us ahead in, say, 5 years. Where will we be with MLT?
That depends. If it continues to be a small-scale laboratory research operation, we'll be farther down the road because some of this can be done without major expenditures and that sort of thing.
Some of it will be done sooner rather than later, by this summer.
Within the next couple of months, what we're doing at the present time is bringing up a separate system, a new thrust balance is basically what it boils down to, in order to exclude the possibility that there is some fluky little spurious effect going on in the present system. The way in which you make sure that that's not the case, there are two ways. One is to analyze the system very carefully to make sure that there's nothing that could do that, which has already been done, and that suggests that it's not a spurious effect. The other way is to make a completely different type of thrust balance and see if you get the same sort of results, and that's
Let's suppose that you're successful in all these sort of things. Where does that leave us?
It leaves you with an effect which can, in principle, at least be scaled to practical levels.
What is practical levels?
Practical levels is a factor of 10 to 100 over what is presently being produced in the laboratory.
And that would be propellantless satellite positioning.
Yeah,
at those
and
levels.
reboost and orbit transfer for
Reboost and orbit transfer.
For smaller satellites, and if you put together arrays of these things and provided adequate power, it could be used for larger satellites as well.
How efficient are they?
The devices that are presently in operation are made from commercially available parts. The commercially available parts have modest loss figures on the order of a few percent. That means you develop heat in these things fairly quickly. Optimization of the devices so that you reduce the losses and consequently heat generation should make them much more efficient. As they presently operate, you run them for a little bit and then you shut them off and let them cool off.
In the efficiency numbers that you want to talk about, you know, you have power plants or maybe 30% efficient, you know, and so where does MLT fit in the food chain for developing thrust or conversion of energy? Where does it fit? Is it the very high end? I mean, there's no such thing as a free lunch, so this is not free energy.
No.
You have to put stuff in.
Yeah.
So
none of the conservation principles of physics are violated by
Right.
this, which means you don't get something for nothing.
Right, and which was one of the things that enamored us with it, because that we didn't buy the free lunch thing. So how efficient is it, do you think it's going to be?
That comes in two parts. One part is the production of the mass fluctuation. This is done by the reactive nature of the electrical circuit involved, which means in principle you can produce fairly large mass fluctuations and put in only enough energy to keep the circuit running. That is to say, overcome the losses within the circuit itself that cause it to heat up and so forth. That can be minimized by optimization of components and things of that sort, materials studies. The other part of it is the energy you have to put in to produce the thrust. That is to say, the magnetic flux which acts on the thing. There, in principle, it depends upon how large a mass fluctuation you produce. Basically, the question then is, if you make it sufficiently massive when you push on it, and you make it almost massless in principle, when you pull on it, your efficiency approaches 100%.
So your devices now are about the size of I would call a red delicious apple.
A little smaller than a red delicious apple.
And
if you go to the hardware store and you buy a can of putty, a 6-ounce can of putty.
Now don't be telling them how to do this.
It's just the Faraday cage that encloses the device.
But something the size of this table then would produce potentially large amounts of thrust.
As a scientist by nature, I'm really hesitant to make those sort of extrapolations on the basis
Does
of what
MLT, when you use it, does it spin or turn? Or is it just basically?
You could hook it up to something that's on an
Spinning,
axle and make it spin if you wanted to, yes.
How far away are we from actually using this on a satellite?
Again, that's a matter of funding. With funding and fast tracking, these could in principle be in use in satellites within 2 to 5 years outside.
Mm-hmm. Could you use any of these things in an auto environment?
That's farther down the road.
Could
Pun
you?
intended.
Yeah.
Let me put it this way. What we're talking about now is a laboratory test device to see whether or not in principle the idea works. Okay. And
Does it work?
Yes, it works. Yeah. But the signals are sufficiently small and the noise is large enough that you have to do signal averaging to bring the signals out and so forth. Okay, so we're talking about very small effects at this point. In principle, those small effects should be scalable to not merely millinewtons or hundreds of millinewtons, or indeed a newton or two, ultimately, for space-type operations, but in principle, eventually you should be able to scale them substantially higher than that. But this depends upon not running into roadblocks, if you will, barriers in the physics that are not anticipated at this point. If there are no major impediments of that sort, you don't run into anything fundamental that says, hey, this is here, but it isn't going to work because of something that you failed to foresee. You know, in principle, you should be able to make them so that you can use them for automotive transport or pretty much anything else you want.
You could. So you're saying that, barring any hooky-doos, let me use my Texas language, that you could use these in automotive applications. Would you anticipate actually running a car with an MLT device? I mean, actually having it go down the road?
If you run a car with an MLT, you can make it into a plane, and if you seal it up sufficiently, you can make it into a spacecraft.
Okay.
That's far down the road, or very, very much up in the air.
20 years from now, or 30 years from now,
Not in
or
my lifetime.
$5 billion from now. It just depends on money or time, right?
It's money and time.
I see.
Yes.
Now, how many devices are in existence that you know of? How many MLTs
How
are
many of them, you're asking how many have I made? A dozen or so.
Okay.
Various different designs.
And how many are in test?
The present devices that are being tested, there are about a half a dozen of them, and they're in various states of levels of shielding. One of the things that you have to worry about this is, since they're fairly high power devices, the ones presently run a 4 kilovolt voltage across capacitors running at about 55 kilohertz. It's a non-negligible amount of radiation is produced by those sorts of things. So what you have to do is you have to button them up, cover them up.
You're
so
talking about
that
radiation.
doesn't go in.
You need to explain radiation. Because
Whenever
some
you
people
have
talk
electromagnetic, whenever you have a current flowing in an electrical circuit, it produces a magnetic field. And when the
But it's
current
not,
is varying, it produces electromagnetic
it's not
waves.
nuclear radiation. It's not nuclear radiation.
No. We're talking about radio waves.
Right, radio waves. Yeah, things that do interference with your radios.
Yes, if you don't shield very carefully, they can louse up
Now,
sensitive instrumentation.
Is there anybody in Europe doing any of these things, or Asia?
There's a fellow in Austria to whom I have sent a couple of test devices, and he's fooling around with them on a time-available basis.
You have a very small group called MLT Research, and I have to disclose I'm part of that intellectual property group. That group is formed by a former graduate student.
He's one of the members,
Yeah.
Tom Hood.
Tom Hood and Paul March.
Yes.
And any others that you'd like to mention?
I didn't get prior approval for public disclosure of their names, but since some of them have spoken in public, the others who've spoken in public, Andrew Palframan up in the Bay Area, and we have an informal association with Hathaway Consulting Services, who's providing specialty designed capacitors, ones that are better optimized than commercially available, that are imminently to be put into test.
So I'm going to go back to my original question. If I had an MLT, why would this audience care?
Why would they care
if
you had an MLT?
I know why I would do it.
Yes, I know you know why you'd care. Why should they care?
Why should they care?
Why would they want them?
Why would they want us to have an MLT?
Because it'll transform the transportation industry is basically what it boils down to.
So it's propellantless transportation. So it's a little box that sits there, and
you put in energy and it puts out thrust without blowing stuff out the tailpipe.
Okay, so there's no emissions outside of an electrical field.
And heat.
And heat.
Yeah.
Okay. And so do you have to give it lots more electricity to get it to do something? I mean, this is one of those chase your tail things? We don't know yet.
No.
Okay.
The scaling law for this particular thing is that the size of the effect in the capacitor scales with the cube of the voltage applied. So if you double a voltage, you get a factor of 8 increase in,
okay. So
which
there's
means higher voltages and higher frequencies lead to higher efficiency. And
okay. So is there any reason why you couldn't stick a bunch of these MLTs, say, on a flywheel of a vehicle and take out the pistons and the rods? And
sure, you could do that, but it'd be much simpler to make an array of them and set them in the engine compartment and just have them do their thing and produce thrust down the road.
Just
You
produce
can
the
get rid
thrust.
of the differential and the drive shaft and the flywheel.
All the parasitic things.
All that stuff. Yeah.
And let's talk about launching something into space. Now, you know, when we see something launched into space, we see basically hailfire and brimstone, and we kill fish, and I don't know what else happens, but it's
Lots
obnoxious.
of stuff comes out the tailpipe.
Lots of stuff comes out the tailpipe, and I'm not sure what it is, and you can't go downwind for some reason. So in this case, let's say you had a big pad, say it was the size of this podium. Is that in your mind's eye 50 years from now? Is that how you see something like this? And it would just accelerate slowly. It wouldn't
the question is money and time. If you can indeed scale them to that level, what you're talking about is orbital access without blowing stuff out the tailpipe, and you can just sort of accelerate conveniently to whatever altitude you want. So
now, would you go at like 1G? Or
you can go at a half a G or 1.5 Gs or whatever.
So it wouldn't be this violent.
No.
Yeah.
No, because
you
you're
wouldn't
not
have to have
creating an
wings, so you're
explosion.
not worried about aerodynamics. You could just push the button.
You could make your craft any shape you want because you wouldn't have to worry about heating it up.
I can imagine Nike wanting something this thin, and the basketball court being 300 feet by 300 feet by 300 feet.
Extra lift for
three-dimensional basketball.
Stick them in the heels.
I could imagine three-dimensional basketball. I mean, you know, from a playing point of view.
Actually, I've not thought of that, but yes, in principle, I suppose you could do that. Could you fit them in the heels of shoes
Yeah, where do you
with
get the
sufficient
energy?
thrust that
Yeah, where do you get the energy?
you'd have to carry a fairly substantial battery pack, I suppose.
Well, we have a few minutes left, and I know this is a very esoteric topic. It's a very esoteric subject, and I asked Mark to bring it forward because it's a world changer, and it is going to happen. So with that, let's bring up the house lights and have about 3 minutes and 40 seconds worth of questions.
Bill Buttinger, what
Please.
happens to equal and opposite reaction? How does that fit into this?
That's exactly what this is all about. What Machs Principle tells you is that when you push on something, the reason why it pushes back on you with the equal and opposite reaction force that you're talking about is because of the gravitational action of mostly distant matter in the universe. That's what Machs Principle technically is. Push on something, gravitational action of the distant matter is the thing that produces a force that you feel is a reaction force. Okay, now, since you've asked that level of technical question, let me take it one step further and anticipate the next question. Okay, if you treat that as a field interaction, which is in fact what Mach's principle says it is, it's a gravity field acting on a local object when you push on it, and you then ask, what are the local sources of that field? There's a standard procedure for doing that. It's called taking the divergence of the field. When you take the four-dimensional divergence of the field, what you end up with is some terms involving time derivatives of masses and things like that. And it's those time derivatives of masses terms that come from the time-like part of relativistic calculations that leads to these transient terms.
So it doesn't change the center of mass.
No.
It simply shifts the entire universe.
In effect,
the
what you're
opposite
doing,
direction.
in effect, what you're doing is you're using the coupling to the rest of the universe to, in effect, push off the universe directly. Okay?
But in very small pieces.
Yeah.
Otherwise,
As I say, there is no real new physics in this. You know, it's just a straightforward relativistic calculation. It's just calculating something that people normally don't calculate. People don't normally ask the question, what are the local sources of this interaction? Okay? When you do that calculation, these time-dependent terms fall out.
there's a really good treaty on, as you can tell, Dr. Woodward is a very personal individual, and so his students have called this the Woodward Effect. He does not like it to be called that.
Mach effects.
But if you Google Woodward Effect, you will find a treaty of all the gory details of math that you could possibly stand.
Actually, I recommend a paper that I published in Foundations of Physics, the October issue of 2004. It's called Flux Capacitors and the Origin of Inertia. Okay? I use flux capacitors in the title as a hook to get people interested. And you'll find that there are two appendices in that paper. One of the appendices, the first one, has a line by line with all of the algebra derivation of the effect. And the second appendix deals with the issue of conservation of momentum.
So what I wanted to ask you is, you've vetted this. Obviously, there's a paper that's published that's been peer-reviewed, and every year you produce a paper, or most every year, for STAFE.
Yeah.
And you might tell them a little bit about STAFE. We have about 10 seconds.
2 seconds.
Okay.
Space Technology Applications International Forum, run by the University of New Mexico every February. For the past few years, I've been contributing a paper to that conference. And so if you go to that website, you'll be able to find those.
Okay. Jim, thank you very much. I
Thank you
appreciate
very
you
much.
for coming. And that concludes the presentation that we have on Mach-Lorentz thrusters.
Yes, and I want to add one postscript. Before I knew how this was supposed to be done, I prepared a PowerPoint presentation, and let me say I'm delighted that I didn't do it. This was much more fun.